Okay, our next topic here is limit theorems, and this is one of our last topics. And we've seen a little bit of this in some examples, but we're going to formalize it a bit here in this section. So sometimes what we can do, and sometimes what we can do, it's pretty useful when we can do this, and we actually do it all the time in statistics, is we might not be able to get an exact expression for a random variable or a collection of random variables. We might have observations that we're modeling as a sequence IID, an independent sequence of random variables, and we're interested in, let's say, the sum of those random variables. That's a common case. And in specific cases, we might be able to we might know the exact distribution of that sum, but in a lot of cases we might not. And but we might be able to approximate the distribution of that sum, provided we have enough data. So that gets to one of the fundamental premises of statistics, which is generally, if we can collect more data, we're better off. Okay, so there are two major limit theorems in statistics: the law of large numbers and the central limit theorem, and we're going to cover both of those. So we've, of course, already seen examples of limit theorems. The Poisson approximation to the binomial is a limit theorem. We called that the law of small numbers or the law of rare events. We also saw the binomial, the normal approximation to the binomial, which is actually a special case of the central limit theorem. So for an example, let's say that we flip a coin. We're going to flip a P coin repeatedly and independently by assumption. And we want to ask the question, how many times is a head tossed? Does a head come up in, let's say, 100 trials or 100,000 trials? So that's one question we're interested in. We can also consider rolling a fair die repeatedly. And what proportion? We ask what proportion will come up as a 6 in a large number of rolls. Or, as is common in statistics, if we suppose we have an IID sequence of random variables, and let's assume that they are normal with some mean and some variance, but we don't know what the mean and variance are, then what is the probability that the sample mean, which I'll define in a moment, the sample mean is within epsilon of the true mean for large N? This is where we're defining X bar N as the sample averages. So X bar N is the average of the first N observations. Okay. So let's do a simple example at first, or at least let's observe that, okay, for this one, so suppose X1, X2, etc. are IID normal mu and sigma squared, then we can actually compute the distribution of the sample mean. We can say that it is normal mu and variance sigma squared over N. how do we prove this? Okay, so we should be able to prove this given the tools that we have. How? Well, because x bar n, by definition, is a scalar multiple and inverse times a sum of independent random variables. And we know the distribution of those independent variables are normal, right? So in particular, we can actually write this as sum of 1 over n times x1 plus 1 over n times x2, etc., up to 1 over n times xn. And we know that the moment generating function, right, the moment generating function of x1 is, they're all the same actually for all I, it's the moment generating function of normal mu sigma squared, e to the mu t plus sigma squared t squared over 2. So then the moment generating function of 1 over n times xi, we can calculate this directly from the moment generating function of xi because it's just a modification by a scalar multiple. So this is actually the moment generating function of xi evaluated at t over n. So we just plug that in here and we get mu t over n plus sigma squared t squared over 2n squared. Okay. So now, how does this play with the distribution of the sample mean? Well, by the multiplication rule for moment generating functions, the moment generating function for the sample mean is the product of the moment generating functions of the individual pieces, which we just calculated. So it's the n-fold product of the same thing, which is e, let me write it as exponential, mu t over n plus sigma squared t squared over 2n squared. And all of that gets raised to the power n, which when we're talking about an exponential comes into the exponent as a multiple. So in other words, we get mu t over n times n. So it's mu t plus sigma squared t squared over 2n squared times n. So it's sigma squared t squared over 2n. And we see that this, it has the form of a moment generating function of a normal. We just have to figure out what are the parameters. Well, it's normal with mean mu. And variance sigma squared over n. And we can appeal the uniqueness theorem because it's a well-behaved moment generating function, which is finite in a region of the unit interval, or in the region of 0. So now, if we, in this case, we actually have an explicit formula, an explicit distribution, so we can ask, okay, what is the probability that the sample mean lies outside of the interval mu minus delta, mu plus delta for some delta, for any delta, for any given delta? Well, we know the distribution of mu bar n, so we just can use what we know about the normal distribution, right? So this is normal mu variance sigma squared over n, so we want to normalize. So what we do is we normalize, so we subtract off the mean, divide by sigma over square root n, x bar n minus mu over sigma over root n, and then mu plus, that should be mu plus delta, mu plus delta minus mu over sigma over square root of n. Well, this is the this is equal in the probability that a normal 0, 1 is between delta over square root sigma square root of n plus and delta over minus delta over sigma square root of n and plus delta for z normal 0, 1, which in terms of the CDF, the distribution function of the normal 0, 1, is 2 times epsilon square root of n minus 1, which is converging, right? So this converges here as n goes to infinity. This is starting to look like phi of infinity, which is equal to 1. 2 times 1 is 1, minus 1 is 1. So 2 times 1 is 2, minus 1 is 1. This is converging to 1 as n goes to infinity. Therefore, the answer to the question is that the probability that x bar lies outside of that region is converging to 0 as n goes to infinity. So in other words, as we collect more and more data, this sample mean is with very high probability going to be concentrated around the mean. It's going to converge to the mean. This is the law of large numbers, essentially. This is, but in the specific case of the normal distribution, or what's also sometimes called the law of averages. Okay, so in this case, we're able to prove it. But here what we've seen is we've seen a convergence, a limit of a probability that is what introduces us now to the concept of convergence and probability, which we're going to talk about next.